So, hello everyone, how are you all? I hope you all are doing and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new, amazing as well as phenomenal video. Believe me, guys, this video is gonna be the phenomenal one actually. And maybe I'm just gonna consider that this video is gonna be the bestest video of mine ever I have made till now, but I'm not sure about the future. But till now, it's the best video because we are gonna relate two great named integrals. Named integrals means like Gaussian integral, Fresnel integral, Dirichlet integral. So yeah, these type of integrals. But today we are gonna relate, or maybe not relate, but prove the Gaussian integral with the help of the generalized Fresnel integral. And what's the generalized Fresnel integral looks like? Here it is. I have written that in tools, actually the first one and the second one. And this one will help us to just reach up to the integrand of the Gaussian integral. And this is incredible. Like literally, just imagine, guys, these things are being related to each other. We are gonna prove the Gaussian integral with the help of Fresnel integral, you can say. So yeah, this is amazing, and I think I should just begin the proof with a very good smile on your face as well as on mine. Okay, so I'm just gonna and now let's talk about the Gaussian integral first. We have proved the Gaussian integral a couple of times, and the last one was the most recent video of mine, I think. Yeah. So basically, Gaussian integral, right? Okay, so it's integral from negative infinity to infinity of e to the negative x squared dx, and the result is pretty amazing, the square root of pi. And since this x squared is an even function, so we can write this as 2 times integral from 0 to infinity of e to the negative x squared dx. So basically we can divide both sides with 2 and we would be having this result. Yeah. So basically we have to prove this thing down with the help of these two things and this one as well. So let's just dive into it because the journey is itself very amazing and beautiful, I would say. It's not scenic beauty, but it's mathematical beauty. Yeah. Okay. So okay, now let's just talk about the Euler's formula. So we have, and I have proved all the all the tools that I'm just gonna use to prove the Gaussian integral. All these 3 things I have proven them. So you can consider watch those things. So Euler's formula. So it's e to the iz is cosine of z plus I sine of c. Okay, and now for our case, let's say z is being replaced with I x squared, right? So basically it's gonna be e to the I times I x squared equals cosine of z's I x squared and plus I sine of I x squared. And since I times I is I squared and I squared is -1, so finally we are having e to the negative x squared equals cosine of ix plus I times sine of ix. And in order to just, I'm sorry, it's x squared, not x only. So don't get confused over there. Yeah, now it's good. So we just have to find the integral from 0 to infinity of this very function. So let's just integrate both sides. So integrating both sides from 0 to infinity with respect to x. So that's going to give us integral from 0 to infinity of e to the negative x squared dx. And on the left hand side, on the right hand side, it's the integral of this function actually. Cosine of I x squared plus I sine of I x squared dx. So for now, let's just consider this integral as g. So g is the integral from 0 to infinity. We can split this this integral into two separate integrals, something sort of this one. The first one as the integral from 0 to infinity of cosine of I x squared and plus I times the second integral, which is sine of I x squared dx. And now if we just got to evaluate these two integrals, we are good to go with our Gaussian integral, right? So we just have to talk about this one integral and this very one integral. And guess what? We're just gonna take the help of the generalized Fresnel integral. Obviously, that's why I've written that big chunk of things over there. So yeah, let's just use them. So firstly, let's talk about the cosine one. Oh, not yet, dude, not yet. Firstly, let's talk about one of these. Maybe let's talk about sine. So we have proven the sine of x to the z over x to the a dx equals 1 over z times gamma of 1 minus a over z and times sine of 1 minus a times pi over 2z. So this is the generalized like Fresnel integral, you can say. When you plug a equals 0 and z equals 2, so you're gonna have the Fresnel integral, and I have done that right in one of my recent videos. Okay, so we are having this one, but look, guess what? If we anyhow plug x equals 2 here and a equals 0, but still we are not having I, so we have to talk about that I. So now I'm just going to use this result actually in order to get that integral. So basically let's consider that integral. So let's say that I equals integral from 0 to infinity of sine of I x to the z. Let's just generalize that integral, because let's just generalize this integral actually. Sine of I x to the z over x to the a and dx, right? We have generalized that one. So basically we're just gonna take the help of that integral and we will generalize this one as well. So let's just talk about this. So for this integral, let's just it's my substitution actually, it's mine actually. And you know what, the whole things that I'm just gonna explain you, it's done by me only, right? I have never used any AI or any external agents to just help me out with this. So yeah, let's just not admire myself. Okay, so basically u substitution we're just gonna take the help of. So it's I x to the z equals t to the z. So this is our u sub, right? Okay, so it's I actually. Okay, now if we talk about the derivative, so it's I z x to the z minus 1 dx equals z times t to the z minus 1 dt. Yeah, this is the crucial part, I would say, and this is quite messy. Not Lionel Messi, but it's messy. Okay, yeah. Okay, wait a second. So let's just talk about this. So from this very equation, we can say that x to the z is t to the z over I. So this is what we have got so far. And from here as well, we can isolate the x as t over I to the 1 over z. I hope, guys, everything is clear so far. It's not difficult to understand that. Okay, so basically let's just plug this x to the z and x over there. So basically we are having I z x to the z times x to the negative 1 dx equals, well, we are getting rid of this z and this z, so we don't need to write that down. And yeah, and it's t to the z times t to the negative 1 dt. Okay, so yeah, it's I, and x to the z is t to the z over I, right? And x to the negative 1 is t to the negative 1 over I to the negative 1 over z, and it's dx t to the z t to the negative 1 dt. And yeah, obviously we're gonna have a lot of cancellations here. This I, t to the z, t to the z, t to the negative 1, t to the negative 1, and finally we are having dx as I to the negative 1 over z dt. Like literally, just imagine all those things, and that's amazing, isn't that, guys? Okay, so let's just talk about that integral. So basically our I is gonna become, and limits are gonna change, like limits will be from 0 to infinity, right? And yeah, so it's gonna be sine of t to the z, because we have considered I x to the z as t to the z. So sine t to the z over, and x to the a. So from here, if we just raise the exponents of this equation to the a, so that's gonna be x to the a equals t to the a over I to the a over z, right? So it's t to the a over I to the a over z, and we are having I to the I to the negative 1 over z dt, right? Okay, and now let's just talk about this integral, and it's pretty easy to evaluate, because this one and this one will be treated as constant, and this is the integral that we have proven earlier. So this is beautiful, obviously, as I just promised you guys. The journey is itself very beautiful. So I is gonna be I to the a over z, and times I to the negative 1 over z, times integral from 0 to infinity of sine of t to the z over t to the a dt, right? And now here, like this integral has this crazy and amazing result. So let's just plug that down. So basically, I is gonna be I to the a minus 1 over z, right? And 1 over z times 1 over z times gamma of 1 minus a over z, just copying this result over this integral, and times sine of 1 minus a pi 2 times z. And you know what? The crazy part is that we have never just bothered, we have never touched this sine function, right? So without touching that, we just got this result. So if we're gonna do the same things that we have done with this one, actually, with for this one, actually, for the second one, the cosine one, so we ain't gonna change the, but like we will not having any other result. Just we have to multiply this I to the a minus 1 over z in this result in order to get cosine of I x to the z over x to the a, and that too from 0 to infinity of integral. So I'm not gonna do that because it's easy and it's noticed, like it is noticeable, I would say. You can notice that. So this is the result. Oh, let me just write that down. Integral from 0 to infinity sine of I x to the z over x to the a dx. Here it's the result, actually. I to the a minus 1 over z, 1 over z gamma of 1 minus a over z, and it's sine of 1 minus a pi over 2z. And similarly, here we are having for the cosine one, we'll just change this sine would be replaced with cosine, and everything, rest of the things will be same. I to the a minus 1 over z times 1 over z gamma of 1 minus a over z, and cosine of 1 minus a pi over 2z. So yeah, we just got those results, right? Okay, so And now in these two integrals, if we gonna plug a equals 0 and z equals 2, so what we gonna get? So integral from 0 to infinity of sine I x squared dx. So basically a is 0, so it's gonna be a is 0, so it's gonna be negative 1 over 2, I to the negative 1 over 2, and times 1 over 2 gamma of 1 over 2 and sine of pi over 4 when you plug a equals 0 and like z equals 2. And similarly we would be having the cosine thing as well. Actually, let me just write that down as well here. And yeah, wait a second. So yeah, we are having, well, sine of pi over 4 is just 1 over square root of 2, and gamma of 1 over 2 is the square root of pi. So basically the integral from 0 to infinity of sine of I x squared dx is also equals to the integral from 0 to infinity of cosine of I x squared dx, and that too equals 1 over square root of I, and it's square root of pi over 2 times square root of 2. Okay guys, so that much thing that we are having so far actually. And now let's just get back to the equation. Integral, actually that was g, so g was representing the integral from 0 to infinity of cosine of I x squared dx plus I times integral from 0 to infinity of sine of I x squared dx. Guess what guys? You can just check that out. Check this out guys. This is the integral and that's the result. And this is the same integral, that's the same result actually. So basically g is coming out to be square root of pi over, it's 2 times the square root of I and times the square root of 2 plus I times the square root of pi over 2 times the square root of I square root of 2. Okay, it's not the Gaussian integral actually, it's not the result, and it doesn't look like the result that I have shown earlier anymore. Like anyways, how can you say that it's gonna be the square root of pi over 2, because we are having some square root of I, square root of 2, and here similarly as well there. So it's not it's unbelievable. But guess what, mathematics and complex numbers are like wow. So basically let's just plug the square root of pi over 2 times the square root of I, the square root of 2 common outside as a factor, and we are having 1 plus I. Okay. Now let's just talk about the square root of I a little bit. Well, we know that I is e to the I pi over 2, right? So I is e to the I pi over 2. So if we're gonna raise it to the power of 1 over 2 in order to get the square root of I, so it's gonna be e to the I pi over 4. And from the Euler's formula, this can be written as the square root of I equals cosine of pi over 4 plus I sine of pi over 4. So basically square root of I is gonna be 1 over square root of 2 plus I over square root of 2. That's gonna be 1 plus I over square root of 2. And now if you're gonna multiply both sides with the square root of 2, so that's gonna be square root of 2 times the square root of I as 1 plus I. Okay, yeah. So now from this equation we can plug 1 plus I as the square root of 2 times the square root of I. So the square root of pi over 2 times the square root of I, the square root of 2, and here we have the square root of 2 times the square root of I. We just got rid of these two things, and we are finally having our g as the square root of pi over 2. This is the beauty of mathematics, like literally guys, whatever I've done, wait a second, and yeah, like just imagine, just imagine from where we began and where we are just ending up all the things. Oh my goodness. And you know what, g was the integral from 0 to infinity of e to the negative x squared dx. So from there we can say this is the square root of pi over 2. Oh my goodness, just imagine, just not imagine, just take a look at these things. Oh yeah, that's amazing, I would say. Oh wow, this is extremely amazing, guys. This is extremely amazing. Oh, okay, yeah, I don't need to be so much happy because it's fine, and it's yeah, it's a thing to be happy of, I would say. But yeah, it's all right, guys. Guys, if you got to learn out of it something, please make sure to like, subscribe, and share. And if you have any doubts so far, you're free to ask me in the comment section. I'll be there to like answer your questions. Don't worry about that. Okay, and I think it's fine. And yeah, we have gratefully done that, and it's amazing. Goodbye, guys. Take care. Love you, and stay tuned for my next videos because I'm just gonna bring a lot of stuff like this. Obviously, goodbye, guys.